Welcome, welcome everyone. Welcome to my PPT. My name is before this recording this PPT. This PPT is recording about the subject applied physics. Before entering into the PPT, let me introduce myself. Myself, Bhuvaneshwar, currently pursuing my undergraduate degree from Institute of Aeronautical Engineering in the Department of Computer Science Engineering. Basically, I belongs to the CSEA section in IRE, and you can see my roll number on my screen, which 2195100527. Without any further delay, let us move into the PPT or tech talk. Today, my whole topic is about topic called fabrication and characterization of the charge plasma. This is in this whole PPT we are going to discuss about this point or this topic called fabrication and characterization of the charge plasma. Okay, without any further delay, let us move into the PPT. Okay, let us first see what are the contents or what are we going to discuss in this whole PPT. In this slide I included what I am going to discuss in this whole PPT or the contents in the PPT. Let us first I will start with the introduction. I will give some brief idea about the topic in the introduction slides, and next I am going to show the experimental procedures for the topic. In the second part of the PPT, I am going to show about the experimental procedures for the topic to make you clear understanding about the topic. At the third, I will show the results of the experimental procedures, which before we perform or write the experimental procedures, I will show the results of those experiments, and then you can get a clear idea and how and why. Later we move on to the discussions, how this before scientists made the discussions, and now we will make we will discuss about the results and the procedures and anything, and later further moving on, at last we will going to discuss the conclusion of the video. I will use some conclusion points, and you go at last some main points or key points about the video. These all are the topics included in PPT. Once you can go through the topics like introduction, experimental procedures, results, discussions, and conclusion. Okay, let us move. See, here it is an introduction slide. Okay, I will start saying the introduction see here, silicon on insulator SOI basic devices with ultra thin body are considered for future large scale integrated IC applications. See here, in this PPT I am going to use the word IC means integrated circuits. Integrated circuit means nothing but it's a chipboard kind of thing, which included a semiconductor devices like silicon IC applications, and silicon PIN diode, PN junction acting as an rectifier is an such component. It plays an important role in diverse research domains like power ICs and light emitting devices. This silicon and insulator based devices plays a key role in IC, which I discussed before, integrated circuits and light emitting devices. It plays main role in the research domain like power ICs and light emitting devices. Desirable diode properties are very low found voltage drop and small reverse leakage current to reduce the power displayed by the rectifier. For conventional PN junctions with nanoscale dimensions, the key issue is doping control. How to control by the doping, doping function using doping activation and obtaining step doping profiles demanding a low temperature budget. This is the whole introduction, which no, it's not the whole, this is the introduction in the slide. I think so you are clear with the slide. Once I let me erase my screen. You can go through the slide once again. Okay. We'll move into the further slides. See here, stocky based device which metal or metal sliced source drain contacts are reported to circumvent these fabrication related issues and produce performance specification comparable with conventional diodes. Shows a semantic cross section to our realized device called the charge plasma CP diode. Like this specialization section of a realized device called the charge plasma diode CP. Here CP means charge plasma diode. In the whole PPT we are going to use CP, which means charge plasma diode. Here two separate metallic gates are placed on top of the thin silicon body. Like it's nothing but two separated metallic gates, like metallic gates and the metal plates are placed on the top of the thin silicon body. The gates are isolated from the top of the body by a dielectric layer, and each forms a contact at one side of the silicon body. So one part of the, like one top of the silicon body in the devices form a contact at one side of the silicon body. In the devices form in this devices presented in this letter, the metallic contacts are extended the top of the thin silicon body in order to reduce the contact resistance. Like in order to resist the contact resistance, they were in the place in the such kind of an order. As stated earlier, there are two essential features in this concept. First, we work functions of the cathode and anode metals should fulfill like consider functions xi of m or pi of pi m pi m c less than x of xi plus e of g by 2, and this pi m comma a greater than xsi plus eg of 2 in terms of electron affinity of bulk silicon xsi 4.4 and the band gap of bulk silicon Eg. Okay, I think so you are clear about this whole slide I discussed just now. Once you can go through the PPT slide once again. Okay, for optical rectifying behavior, the difference between both work functions should be at least equal. Like at least it's not at most, at least it means like it can vary from 0.5 to infinity, or it's here it's at least 0.5 means it can vary from 0.5 electrovolts to infinity electrovolts. Second, the thickness of the silicon body should be around or less than the debye length. Like debye, the units of debye. No need to say once again. Like it's a small issue. For this situation, the charge underneath both gates in the silicon is primarily determined by charge carriers, and the depletion charge can be neglected irrespective of the doping concentration in the silicon layer. Here we can and the depletion charge can be we can neglect it with respect to the doping concentration in the silicon layer. This letter deals with the fabrication and electrical characterization of CP diodes. Like this whole PPT deals with the fabrication and electrical characteristics of the CP diodes. We will show that the CP diodes can perform comparably with conventional PN junction with doped regions by making a wise choice of metal combination and device dimensions. Here we will show the CP diodes, plasma diodes, characterized plasma diodes perform comparably with conventional PN diodes or junction with doped regions by making a wise choice of metal combination and device dimensions. I hope you understand this slide too. This is the whole introduction which I am giving in this whole PPT. Let us, without any delay, we will move into the another slides. Here, this is the experimental procedure I am going to discuss. Experimental procedure: a device fabricated using 4 in SOA welfare with a device fabricated with 4 in foreign SOI wafers with A1 macro buried oxide BOX. Okay, the devices are fabricated using foreign SOI wafers with A1 macrometers buried oxide BOX and at most eccentric 6.1014 centimeters inverse NIC layer of 340 nanometer thick on top. The top SI layer was then thinned down to 25 nanometers by thermal oxidation at 950 degrees centigrade in a quartz furnace. Like quartz furnace means like silicon oxides, which are like the quartz metal, like it's a silicon based metal, like quartz compound, silicon based compound. Quartz furnace under oxygen ambient. The thinned down SI layer is patterned in 30% thermal methyl ammonium hydroxide solution using a silicon oxide mask. After cleaning and removal of the oxide mask, a 10 nanometer thick gate oxide was ground by thermal oxidation at 950 degrees centigrade on clean silicon surface, resulting in a final SI thickness of around 220 nanometers. Later, the metal contacts are then made to form the anode and cathode. The choice of contact metal is based on their availability in our clean room facility, ease of process integration, the extracted stocky barrier is to low doped bulk Si. For the device described here, we choose palladium, a metal with high work function. Like work function is for like work function amount of work done to bring an electron from the metal. Like this is called work function. 4.9 electron as an anode erbium with low work function. Like you can see here, it's just varies in the points. Even it's varies in the point, it's showing tremendous effects in the experiment. So we should take care of the approximation or errors while performing. Like high should be exactly 4.9 or it can be more than, and low should be 4.4. It should not exceed 4.4 as cathode. Both metals were sputtered immediately after an HF dip to minimize residual oxide. No thermal treatment was applied after sputtering. Care should be taken that measurements do not exceed 400 K. Like we should definitely take care, and the should not exceed, like temperature should not exceed 400 Kelvin due to the onset of PD siliconation at temperatures of as low as 300 K. I think you guys understand this. It's not complete up still now. I hope so that you guys understand this whole experimental procedure, and we will continue. Increasing the measurement temperature or the time result in PDI to SI formation observation as a slight increase in the increasing the measurement temperature or time results in PD to SI formation observation table as a slight increase in the reverse current due to the lower work function of PD to SI, like lead silicon metal 4.8 electron volts. Aerosolidation is reported to significantly reduce the stocky barrier height. We have not observed inabilities in the ER contacts, but material analysis could not exclude possibility of ER sediation. In figure 1.b, I will show the graph below. The top view image of the device on wafer is shown as through a microscope. Shows a cross section of fabricated device obtained using transmission electron microscopy. TEM electrical characterization was carried out on SUS Microtech PM300 manual probe station equipped with Keithley 4200 semiconductor calibration systems. Now let us see the results in the discussion here. The electrical characteristics discussed here are for the intrinsic silicon area of 10. Remember this value, 100 into 10 nanometer square, and metal spacing of 3 nanometer unless specified otherwise. We began by investigating the symmetrical device structures in which the same metal was employed for an anode and cathode, either PD or ER. From these structures, we investigated the MOSFET behavior by using substrate as backgate. The cathode was kept at zero. We kept the cathode at 0 volts, and the anode voltage VAC was swept from 0 to 1 volt, and the gate voltage VGC was stepped from 0 to minus 30 volts. The resulting output characteristics are shown in figure 2. High gate voltage had to be applied because of thick 1 micrometer box layer between the substrate and the SOI layer. The LAVAC output characteristics of the ERR devices show a linear behavior in the linear region, indicating good ohmic contact. On the other hand, the PDPD devices have diode behavior in the linear region, confirming the stocky the Schottky effect, like stocky behavior of this contact of lower doped n-type silicon. Now here you can see the graph, like you can observe the graph like which was the potential V of anode into a micrometers, like units are from 0 to 0.8, 1.6, 2.4, 3.2. Here while VGC increases at that constant temperature, from here it's vary from 0 volt to minus 30 volts. Here it's 0, and we keep 5 volt per step. We gradually increasing 5 volts for every step, 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 30. Like here, here it's between 5, 10, 15, 20, 25. Here at last 30, increasing 5 volt per step gradually at constant temperature 300K, where Vg is equal minus 30, and microampere, like we increase from 0.4 to 0.4, like 0.8, 0.8, 0.8. Here x-axis we took V of AC. Then the graphs here VGC like decrease with voltage decreasing, like minus 30 volts per every decreasing, minus 5 volts for every step. Here we plot another graph by using the experimental procedure, where we take VGC as 0 to minus 30. Like before we decreased, but here we are like increasing in the opposite of the axis. Here 0, 5, 5, 5, 5, like 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. It's in the negative sign, and gradually increasing the minus VGC and taking the x-axis, and here 1 into a power minus 10 micro units. We upload the plotted the graph. You can see I will rub the lines, and once again you can see here. Once you can observe the graph for 1 minute, while 1 minute. Okay, we will move on to the further slide. Okay, here next we examine the CP diode. The cathode ER side and the back gate are kept at 0 volt. The anode is biased with VAC equal to minus 1 to 1. Figure 3 shows the temperature dependent LAVAC characteristics of a diode under the aforementioned biasing condition. The diode shows rectification in the whole range from 288 to 398K. In contrast to the convention of PN diode, the O1 current increasing exponentially with the temperature, resulting in an ion or IOF ratio of 105 to 398K. Only 2 orders of magnitude of reduction with respect to the 107 at room temperature. At room temperature, the increasing ion is attributed to the on current being limited by diffusion, since the gates are in weak inversion mode at high forward bias. At RT, a small and almost constant leakage current of around 1 Faraday ampere per micrometer is obtained, which indicates a low density of active generation centers in the bulk silicon body.
ఇక్కడ 24 hours pattern లాగా.
Here you can observe the another graph which was plotted between the voltage V and current IA, where units are ammeter per voltage, like ammeter per micrometer. Here we started from -1 to 0. -0.5 to 0.5, like every 0.5, where we kept VG is equal to 0 volt and temperature 300 K. You can observe that the clad first, like gradually upon decrease, like it's decreased gradually, like first it's like a straight line and it's decreased, and straightly it's increased like exponentially. You can observe the graph, like which even you can observe the black line or red line which I drawn. This is the graph obtained. Like on x-axis it's are in the 10 power minus 7, like 10 power minus units. And here this also gives and confirmed that the region under the PD metal gate acts as an P or PI region, under the ER metal gate as an N or N plus region, and hence forming PI and diode AI on or off current ratio around 107 and a current swing CS of around 88 MV per deck to zero substrate. Bias is obtained. The CS depends on the quality of SI or SiO2 interference. The presence of interference traps tend to degrade the fast switching of the diode from off to on state and hence result in poor CS. By applying a suitable substrate bias, it is possible to determine whether the interference traps at the box or SI interference plays a role in weakening the CS, form the ideal wave of 60 MV per deck. On varying the substrate bias from 0 to -30 volts, it can be seen that the CS changes from 88 to 68 MV per deck. No hysteresis was observed in the device characteristic. No hysteresis losses interchanging the anode and cathode were reported to give a shift in characteristics of CNTS. We do not see in our devices. See, we have fabricated a new rectifier called CP diode. This is the conclusion for the whole PPT. Like we have fabricated a new rectifier called CP diode that makes use of function difference between the metal and contact and elastic silicon body. The novel device requires no doping, avoiding the statistical doping, fabrication and doping control issues, and it can be proceeded at low temperatures even. Or experimental results show that the high on and off current ratios both at RT, it means room temperature 107 and evacuated temperature 105, combined with a low leakage current 1 farad, like 1 ampere per nanometer at room temperature, are possible to achieve using the technique. It is expected that compared with conventional diodes, the on-off ratio at elevated temperature is order of magnitude better due to exponential increase in on current. Better CSS can be achieved by reducing interference traps between SiO to SI interferences by using the symmetrical metal contacts and substrates as black gate. MSOFET like cancellation can be obtained. Thus a new way of making rectifiers and MSETs and CMOs, MOSFETs and CMOs compatible manner is introduced. Okay, I hope so. You everybody understand the whole PPT, and I discussed every point which I kept in the content. And thank you everyone for being the part of the whole video and the PPT. Thank you. If you want this PPT, you can download from my description. I will provide the link here. Thank you.